Okay, so first up in our tour of radical reactions, we're going to do radical bromination. I think this is kind of the simplest case of radical mechanisms. We'll talk about the parts of the radical mechanism, what are the things that we look out for, how do we consider what's stable, and all this other kind of stuff. Radical mechanisms are different from SN1, SN2 reactions. They're different from addition reactions, and so we're going to have a slightly different way of thinking about how they work. So get ready. Radical bromination. Okay, so radical bromination is when we're going to start with Br2 and light. And these will always be the conditions. We don't really ever use chlorine for radical brominations, and the reason for that is that chlorine radicals are so reactive that they don't kind of follow the same rules that bromination reactions do. So we're almost always going to use Br2 and light. So I'm using H nu to represent light. Hopefully that's clear, right? This is light, so this is just a way to put in energy. And what's going to happen is step one of every radical bromination is going to be hemolysis of Br2. Right? So almost every reaction, every radical reaction is going to start with the fragmentation of a sigma bond, right? Radical reactions almost always start with a sigma bond between two heteroatoms. And remember, heteroatoms are non-carbon, non-hydrogen atoms, right? Um, fragmenting, right? So this sigma bond between two non-carbon atoms, bromine and bromine, is going to fragment, and each bromine is going to get a single electron. This is homolysis. Homolysis is lysis is breaking, homo is the same, and so they're breaking in an equal manner where each bromine gets a single electron. Now this, of course, is very different from every other mechanism that we've done to this point. Every other time we've done a mechanism, we've talked about find the lone pairs, find the pi bonds, right? Use those two electrons to make new bonds somewhere else, right? The radical reactions, that's not how we think about things. And so radical reactions are very, very different. We kind of have to throw away all the acid-base stuff that we've done before, all the nucleophile and electrophile stuff that we've done before. We're not going to think in those terms anymore. You won't hear me use ideas like acid, base, nucleophile, electrophile when we talk about radical reactions. Instead, we're going to be completely consumed by, or completely concerned only with, how do we make a radical stable, right? We're always going to be moving towards what's the most stable product we can make in each step of this sequence, right? So the first thing that happens is we generate our radical, right? So these radicals are single electron, single unpaired electrons. That is what makes it a radical, right? So whenever you have this single dot on bromine, or anything, a single dot on anything, that makes it a radical. Now notice these bromines have lone pairs as well. I just haven't drawn them in, right? Each bromine will have 3 lone pairs on it. So each bromine overall has 7 electrons. Since bromine is in group 7, that means that the formal charge of these bromine radicals is neutral. We're not creating a formal positive charge or a formal negative charge in these bromines. They're neutral, but obviously they would like to have a full octet, and so they're still pretty reactive. So radicals in general are reactive, which is good because we want to do reactions with them. But anytime you see Br2 in light, the first thing you're going to do is fragment that bromine-bromine bond, make some bromine radicals. Once you have a bromine radical, oh, this is the initiation step. Step 1 is always going to be initiation. We go from having no radicals on the starting material side to having radicals on the product side, right? That's an initiation step. We start with no radicals and we create radicals. Now the question is, what do those radicals do? So let's do an example. We'll start with this compound. We'll treat it with Br2 and light. Right? And we know that the initiation step is going to give us bromine radical plus bromine radical. So that was what we did on the previous slide. The next step, we're going to start with this radical, and this radical wants to not be a radical anymore. So what it's going to do is it's going to find the weakest bond it can and break it in order to no longer be a radical. And so this bromine radical is going to bring one electron over, and it's going to pull one electron out of this sigma bond. Right? So notice I'm using these single-headed arrows to show that only one electron is moving. Right? So if we drew a normal arrow, that would show that there are two electrons moving. With a single-headed arrow, we're only moving a single electron. And so in this case, what we're going to do is we're bringing this bromine together with this hydrogen. Each of those atoms, the bromine atom and the hydrogen atom, are bringing along a single electron. And so what we're going to create is HBr with a sigma bond between the hydrogen and the bromine. So we've taken a single electron here, that's one electron, a single electron here, that's two electrons, and made a sigma bond where those two electrons reside. Now, there were two electrons in this sigma bond, and so we have to kind of track where the other electron goes, and that electron just goes onto that carbon. We end up with a single electron on a tertiary carbon here. This is a tertiary carbon radical. Okay, so whenever we make something weird like this, once we start putting stuff onto carbons and talk about tertiary, secondary, and all that other kind of stuff, you start to wonder, well, why that carbon, right? Why wouldn't I put the radical at a primary position or a secondary position? Why did I pick the tertiary position, right? And the basic the rule is it's the same as carbocations. If you're going to remove electrons from carbons, you want to remove electrons from the carbons that have the most other electrons surrounding them, because then you're not creating a super electron deficient position, right? Because that position doesn't lose as much electrons because it's got all those other electrons around it surrounding it. And so for the same reason that tertiary cations are more stable than secondary cations, tertiary radicals are more stable than secondary radicals, right? So tertiary radicals more stable than secondary radicals. Secondary radicals are more stable than primary radicals, and primary radicals would be more stable than a methyl radical, right? CH3 radical. So we can use the same ideas here. So radical stability right, goes with substitution. Tertiary radicals are more stable than secondary radicals, are more stable than primary radicals. Most stable? Least stable. And then the other thing that affects radical stability is resonance, right? And we'll talk about that when we get to the allylic bromination reaction. In this case, we don't have to worry about resonance because there are no pi bonds in this molecule. But the upshot of all this is that we almost always form a carbon radical at the most substituted position. Right? So in this case, we have a bunch of primary carbons. Every methyl group is a primary carbon. We have a secondary carbon here, and then we have a tertiary carbon that's kind of the central point of this molecule. And so the tertiary carbon is where we make the radical because that radical will be the most stable. Now this radical, of course, doesn't want to be a radical, and so it's going to go find the weakest bond it can and break it in order to pick up another electron. And so what it does is, of course, this picks up an electron from the bromine-bromine bond. And again, we're breaking this bromine-bromine bond. One of those electrons is going to react with this carbon, and so this carbon and this bromine are going to end up connected to each other. So we get our product, over here where this bromine ends up here. And the other product we get is a bromine radical. And so the kind of the result of this whole reaction is that whenever we do radical bromination, whenever we have Br2 in light, we're going to take the most substituted hydrogen, the hydrogen attached to the most substituted carbon, we're going to remove that hydrogen and replace it with a bromine, right? The nice thing is we don't have to worry about rearrangement, because if we take the hydrogen from the most substituted position in the first place, that means that we're already creating the most stable radical. So with radicals, we don't have to worry about rearrangement. We don't have to worry about kind of where else can we put this, because it's always going to form the most stable radical it can. And once it forms that most stable radical, it pretty much immediately reacts with Br2 in order to pick up this bromine and make a tertiary bromide, right? So this is the final product of our organic compound. We started with 2-methylbutane. We end up with 2-bromo-2-methylbutane. Now, the cool thing about radical bromination is that the product that we make here, right, the bromine radical product is the same molecule as the product of the initiation step. So this bromine radical is the same thing that we use to kind of start this whole reaction. And so basically, once we do this initiation step once, we don't need to do it again, because these bromine radicals this bromine radical goes in to react with the organic molecule, and the end result is that we get another bromine radical out the other end. And so this bromine radical can then go find another equivalent of the organic molecule and start the whole process over. Right? This is called, of course, a chain reaction. So whenever we have our products equaling our starting materials, that means that we have kind of a circular reaction where we start here, right? We do our reactions, do our reactions, do our reactions, and then in the end, we end up right back where we started. And so we can just keep cycling through this, and we'll keep producing more bromine radicals until eventually all of the bromine, all of the Br2 is consumed. And then we can't produce any more bromine radicals, and the reaction stops. Okay. All right. So the take-home message here, what is the point of radical bromination? The point of radical bromination is we can take a compound that has no functional groups, right? There are no alkenes, there are no alcohols or anything here, and we can introduce a halogen at the most substituted position by doing bromination, right? And so then, of course, if we think about this from a synthesis perspective, once we have that halogen on there, now we can do things like SN1. E2, E1 reactions, right? We can make alkenes if we do an elimination reaction there. And depending on what type of base we choose, we could either do follow Zaitsev's rule, not follow Zaitsev's rule, right? We could do eliminations to make alkenes. Once we make alkenes, we can do all kinds of things, right? We have a whole bunch of reactions that we can do there. We can do substitution reactions. And so if we want to get rid of that bromine and replace it with a sulfur or a nitrogen or an oxygen, right, we can do SN1 reactions in order to get to replace that halogen with other things. So making halogenated compounds is important because we can use those then as starting materials for the next step in the sequence and start to make other things. Okay, so the next reaction is going to be the addition of HBr to pi bonds in anti-Markovnikov matter.